to this event today with healthy condition. Okay, before we start the lecture sessions today, let's pray based on our religions, and praying time can be started now. Finish, and let me introduce you today our speaker, Mr. Dr. Hairil Anas bin MD Rizali. Yeah, he's the part of Sound and Vibration Research Group from Department of Mechanical and Manufacturing Engineering, Faculty of Engineering, University Putra Malaysia. And he was pursued his PhD in Sound and Vibration, Institute of Sound and Vibration, University of Southampton, UK. And some of his areas of interest are mechanical vibration, biodynamics, ergonomics, and etc. And right now, he has some affiliation at graduate member, Board of Engineers Malaysia, member of Society of Automotive Engineers, and etc. And there are some appointments right now that he has. There is Secretary General, Society of Vibrations and Acoustic Malaysia, and then Deputy Technical Manager and Approved Signatory, Metrology Laboratory, Department of Mechanical and Manufacturing Engineering at UPM. And there are some publications that he already pursued. There are 22 right now that shows in your CV, right? There are 22 that he shows in the CV, and here is the research that he already done. And yeah, he is our amazing guest lecturer today. And give applause to him right now. And we welcome you to be our speaker today. The time is yours.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera and good morning to all of you who attend this guest lecture. All right, thank you also to the Mr. Speaker, MC, Master of Ceremony, also all the docent, okay, as well as other guests. Okay, so the topics that I want to talk today is something related to what I've done recently, but in a way that since it is still not yet, it is still in progress, then I'll try to make it like something like sharing session instead. And I divide it into two aspects, which are the ergonomic aspect and the statistical aspect, since I've been tasked to give you a guest lecture in something related to ergonomics and statistics. So what we have here is today is a combination of both studies, so that maybe at a later point that you are going to work and apply these courses or knowledge, you have some kind of understanding of how it is being done. All right, so maybe I've got the next slide. Oops, I've got to turn it on. Aha. This is much less information than the one that the MC has been given. And a different kind of picture here. Different kind of picture here. And now this is me. Okay, I think I'm have gained some weight. Yeah, boleh. Okay. If you see here, my field of expertise is in the field of sound and vibration, and I think the MC already mentioned about it, that the area could be anything related to sound and vibration, all right? Actually, it's anything related to sound and vibration, and I actually currently working at the Department of Mechanical and Manufacturing Engineering. I did a lot of work in the aspect of economics, especially in terms of human vibration and sound. We do a lot of consultancy measurement inside of cars, okay, on-site in industry. And one of the aspects that usually they ask me as consultant is that they want me to analyze sound exposure, okay? And then the sound exposure is actually under one of the regulation in Malaysia. It is also a topic in ergonomics, all right? And one of the common issues that they have is that they want to do the monitoring of noise, to measure the noise, pengukuran bunyi, but they don't have the equipment, okay? And because of that, they asked the institute, the Malaysian Institute of Health and Safety, to do some kind of evaluation of mobile phones' suitability to do measurement of noise. Okay, so that's where we come to this topic, and I think it's also important for me to share to you guys over here. This is a recent thing in Malaysia, but the study has been done by some colleges or researchers outside. So I will try to basically explain to you what is sound and noise. I will show you how it is being calculated, what are the factors and everything. And then you might have some kind of knowledge what is sound and vibration. Sound and noise. So my background is sound and vibration. But actually sound and noise, the core is vibration. All right, so it's actually related. So yeah, that is another story. But yeah, so we look at the ergonomic aspect of sound and noise. And then we look at how to do measurement, how to do some calculation and analysis and presentation of data and the legal requirement in Malaysia. And I've talked to some of the colleges here, docent, and they say that the requirement or the legal requirement here could be the same, except that the way that the authority enforce it could be different in terms of what they do have to do, who are going to be responsible and things like that. So since I'm not that familiar in legal requirement in Indonesia, so I think I better just explain to you what is the legal requirement in Malaysia. But you should have some ideas, could be how it should be. All right, and then we will be looking at how sound application in your mobile phone can be used to do measurement of sound. So you see that I have a different phone than you guys, maybe the same phone, and some of you might using some different phone of Android and iOS. The thing is, they are not the same, they are not built the same. They have different kind of microphones and computational power. That leads to a different kind of measurement or variation of output. So we will discuss about that, and you see at the end, you will have the knowledge of whether you should be using your mobile phones for the monitoring of noise exposure or not. And then later you can use that information for when you're working. All right. Okay. I think I'm not. This chair is a bit not that high, so I'm not sure if I can. Yeah, usually give some kind of talk standing at rostrum, but it's okay. Is it normal that I sit, or should I just? Yeah, it's up to me. Yeah. All right, that's good. So I think I'm more comfortable to be speaking standing because I can see you guys at the back. Those who are. Maybe you guys have some questions, okay? Yeah. Oh, so I can walk. Yeah, is it? Yeah. All right. That's good. That's good. So that I can have some interaction. This is not one way, okay? Guest lecture. Yeah. Usually guest lecture is a one-way thing that I talk and you guys are just listen. But I do hope that if you have some kind of questions, you can just straight ask, okay? So that you don't just put inside of your mind and head and then just leave it after this. Okay, so if you have problems, cannot understand, just straightforward ask me. All right, so we can have a two-way communications. All right, so sound and noise, basically something that it is actually under ergonomics. So one part of it, that when you want to design a workstation, you've got to consider the sound and vibration aspect. All right, because why? Because it will affect your mental. All right, and in Malaysia, the exposure of sound is quite severe, meaning that we've got some workers who are having deaf, okay? And this is really prevalent, meaning that it's like so we've got 365 days, we've got like 10,000 reports, okay, related to deafness. And that means that so every day there are people who are going to be deaf. So we have a legislation to make sure that the employer has the responsibility to measure sound, to make sure that the workers are in good condition at all times. So that's where you are going to be looking at. Okay, so as you are learning here, you learn about ergonomics, and I guess that it is relevant to you. All right, so we go to the first part. Okay, so the outcome of this, is that at the end you should be able to differentiate noise and sound and how they are being presented. All right, so at one point, maybe you are the employer and you are going to employ workers, and you've got to assess their working condition. All right, and one of the way is that you have to make sure the sound is low. All right, and you should know how sound is being measured and presented. So this is where I'm going to show you a little bit about it, but maybe not too detailed, because if you are going to be a sound engineer or sound executive, okay, health and safety executive, maybe you should go to a certain kind of training more. So this is just like a basic things. And then we will look at some minimum requirement legislation in Malaysia. And then I'll try to show you the part of the statistical aspect where you should know at the end the efficacy of mobile phone in measuring sound and noise. Okay, efficacy is whether your measurement is precise or accurate. Okay, what you want is to expect is that when you do measurement, you want to know is it accurate, and also is it precise. All right, you can have a measurement that is precise but not accurate. Maybe you should be measuring 70, all right, but you've got 75. That is not accurate. But all your measurement, you're taking 10 times measurement, they are all precise at 75. All right, so I will show you that. And we're looking at the aspect of also the use of statistical analysis. Okay, you already learned about Z-score, hypothesis testing. Have you all learned hypothesis testing? Semua sudah belajar hypothesis testing? Yeah, because I'll just teach one of the class here about hypothesis testing, and if you are not, maybe you can just listen and maybe try to understand. All right. So hypothesis testing about using Z-score. Okay, Z value or normal distribution, and then we've got t-test, and then the rest. All right. But in this case, we are looking at one sample and comparing the mean. All right. Okay, it's already 10 minutes, so too fast. So I've got like 2 hours, maybe a bit more. I'm not sure if I can finish everything on time. Okay, so we go straight to the introduction to sound and noise. So sound and noise, they are actually coming from the core thing that is something that you measure the same thing, but it has a different kind of definition. So sound is that energy that is transmitted by pressure variations, all right? And air particles vibrate, compression and rarefaction, and generate pressure waves in the air. Okay, if you're learning about physics, you should be learning about sound. Okay, it's actually the vibration of air molecule, all right? And sound is actually the same as noise, but we define it differently. Because why? Because noise is something that you do not want. Sound is something, it may be that something that you want. For example, when you go to eat at a restaurant, okay, you can hear the background noise, right? And it creates some kind of theme, all right? And you feel that, yeah, this food is good, right? Because of the sound helps you to things like that. So at that point, sound is something that you want. And then you put your earphone inside of your ear, all right? At the back, you put inside of your ear, okay? Maybe you do not want to environment to affect you. So you increase the volume and yeah, that sound is something that you want. But noise is something that you do not want. So what is something that you do not want? An example. Any example? Something that you do not want? Sound. Let's say a motorcycles, okay, pass you, okay, they try to increase the sound. Vroom, right? You do not want that. Some of the men, they maybe say, yeah, that's good. Okay, it's like a Lamborghini is just crossing in front of you. Can you please make a sound? Yeah. So that is something that you want. But most of the time, okay, even in Malaysia, we don't have Lamborghini at all times. So most of the time, you do not want the sound of the car passing through you, okay, because it can affect. Because you are concentrating to read something, and suddenly a motorcycle with some high pitching noise cross to you, and you do not want that. So that is noise. You do not want it, okay? So it is still coming from the definition of sound, meaning that there's some molecule of air that is moving up and down, but you do not want that pressure variation. So that is noise. So if you are being exposed to a noise for a very long time, it can affect to you. You can get deaf, okay? And usually we characterize it based on 3 P's. So volume, okay, which is loudness, all right? So you put your earphone in your ear and you increase the volume, okay? You can turn it down or you can turn it up. So that is volume, that is loudness. And then you can characterize it based on pitch, okay? So you go to, maybe some competition of music, right? So your pitch is not good, right? So because of the way the musician, the singer raise their voice, not good, the pitch, right? It's actually frequency, okay? Frequency. So high pitch, that is high pitch, high frequency, or low pitch or low frequency, yeah, that is low frequency. So we characterize it based on frequency, okay? And we also characterize the likelihood of hearing damage is based on time. Okay, you can be at this room, and maybe you stay over there, okay, and I'm speaking too loud here. Maybe the speaker is too loud, so you could be here for 2 hours, right? Or 8 hours, and 2 hours may be okay, but 8 hours is like, oh, I think my mind will get affected. Okay, so we characterize that based on time too, all right? So here inside of your ear, you've got 3 pits, okay, 3 sections. The external ear, that it will catch the pressure variation into your ear. And then you've got the middle ear, will moderate it, okay? And then you've got the inner ear, basically, where you've got a cochlea, okay, something inside of your ear that will vibrate because of the pressure variation. All right, sound is vibration actually, and the cochlea, wherever inside of this inner ear, will capture the sound pressure, sound variation based on vibration. Okay, that vibration will be characterized by your brain, and then you can hear the sound or noise. So that is how it happens inside of your ear. And because of that, our ear has limitation. Okay, our ear here has limitation that we can only hear between 20 to 20 kilohertz. 20 hertz to 20 kilohertz. 20 hertz is something like really low bass, something like that. And 20 kilohertz, I cannot do it. Somebody who are singer here, maybe maybe not 20 kilohertz. 20 kilohertz is really high. Usually, if you sing, it may be in this region of between 125 to 6,000 or 8,000 hertz only. Okay, if you sing, high pitch is actually in this region. Your your equipment, instrument, could be really high. All right, so that is where we do evaluation, okay, for sound in human. So we cannot hear anything less than 20. We cannot hear anything greater than 20. And if I'm becoming older, my sensitivity will becoming less, okay? And usually it could be up to 10 kHz, maybe 10 kHz, maybe. So that means that I cannot hear anything beyond 10 kHz. I hope that you guys can still hear it because you guys are still young, all right? So could be test, okay? Just open some YouTube, okay? But you need a good speaker, okay? Some speaker they cannot do 20 kilohertz up until maybe 5 or 6 kilohertz only. So that's why you can buy speaker that could be really expensive because it can do up until 20 kilohertz. Maybe less, not maybe kilohertz, but yeah, you can try it. And we are most sensitive at frequencies between 500 to 4 kilohertz. Okay, so that is where we measure. Okay, for me, I go to industry, I do measurement of sound. Okay, we only focus much at this frequency of 500 to 4 kilohertz. All right, so that is also where we talk. Much of our sound, okay, coming from my mouth is between 500 to 4 kilohertz. All right, so we can classify the sound based on these 6 types. Okay, if I go to the machine, that machine in your company, whatever that you are going to work, will produce a sound. Okay, that sound could be like or so you characterize it. All right, you characterize it, and it could be steady state, basically pump, like a pump that you have in your house, or over here we've got pump, we got aircon that is rotating at all times. So you can classify it as steady state and continuous. Like right, this is steady state. Okay, and suddenly if the aircon broken, it becomes that is something is broken. Then you classify it into a different kind of sound. Could be steady state, intermittent noise. So you've got to classify it, okay? Because as us, the people who are doing the evaluation of noise, we have to report it based on what kind of sound it is. So if you are working in a civil places, okay, construction, your sound is not continuous. So your sound could be impulsive because sometimes you're using hammer, pung, pung, pung. So you classify it as impulsive. All right. So there are ways to categorize it. So these are the common one. All right. Let's take a look at this table. Okay. I hope that one at the back can see. All right. So if you're working, okay, and in your work area, you've got a forklift, okay, and you are actually driving the forklift, okay, and you see that the noise is 70 dBA. So this is somebody already measured. Okay, it could be greater, okay, it could be less, but commonly it's about 87, okay, 7 dB. And the highest here, you can see that chipping concrete. Okay, chipping concrete. How do you do chipping concrete? Maybe you got a concrete and then you chip, pung, 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 maybe something like that. And the sound is 102.9. So this is common sound, typical level of occupational noise. So if you're working with some airlines, okay, you are doing the maintenance of the airlines, okay, you could be exposed to a greater sound, okay. A jet sound could be reaching 150 dBA. you're working really close to the engine of the aircraft, could be 140, 130. These are normal. Okay, grinding, welding, screw gun, chipping gun. Okay, but if you see here, most of the sound they are greater than 90 or greater than 85. So I will show you after this that the legislation in Malaysia, you cannot be exposed to sound greater than 85. So if you are right now, I think that those people here, you are actually being exposed to sound greater than 85. But there are a limit, okay? You cannot be exposed to sound that is greater than 85 dB for 8 hours for 7 days throughout your work. Okay, so that is the case. Because if you are staying here for all your life, maybe 2 years, you can get deaf just by hearing I'm talking like this. All right. So please bear in mind those who like to use earphone. Okay, you're actually exposed to a greater sound, and if you're doing it every day, you can get deaf. Okay, we're not talking about you cannot hear people are talking, but maybe some noise you cannot hear, like a pitching noise. Okay, we're talking about that. So please bear in mind. Okay. So when you are being exposed to a noise for a very long time, okay, you will get deaf. That is the most damage things that you can have. So here you've got 3 kinds. I categorize it into 3 kinds. So first is tinnitus. All right. So I guess that if I just stop like now, you will see some buzzing noise. Okay, but it is still okay for you. But those who are having the problem, they could get that when there is no external sound. All right. So that is the case. And then hearing loss, that is just I told you. Permanent is the damaged one. And then you can have temporary hearing loss, acoustic trauma, short-term exposure to very high level noise. Okay. And then you can have other health problems. This is what I just maybe in my class yesterday. Is it yesterday? Yesterday, right? I just told you that you can affect the heart rate. So if you are already studied about ergonomics, about workload, okay? So one of the aspects could be increase of heart rate, meaning that you are actually doing some heavy tasks just by hearing the noise, all right? Breathing rate, hypertension, sleep disturbance, lack of concentration, fatigue, and aggression. So if you want to create a good workspace for your employee, then you have to make sure that the sound is low. Okay, otherwise they will get hypertension and affect the productivity. Okay, so effect of noise again, effect of noise on body, you've got physical stress reaction, long-term health effects, psychological effects, all right? That could be stress, anxiety, reduced concentration. Can you guys see it? I know the so one at the back, maybe they cannot see it. If you cannot see it, maybe you can come to the front. But yeah, maybe you can use something else, some device. But so we have also effect of noise on company. So this is for you. This is company misunderstanding. Like I just told you, maybe because of there is no acoustic panel inside of it, acoustic treatment inside of this room, that whenever I talk, it will deflect. And because of that, you cannot hear better, okay? And that is misunderstanding, miscommunication, okay? Auditory fatigue, so 2 hours talking like in this room, maybe you can get fatigue, okay? So that's why after you get back to your hostel, you just sleep. Because you get fatigue. You hear, they listen to me, it's not that clear, and then you try to get it, all right? So you can get fatigue, just like that, all right? So it's okay that you get home and then you sleep, all right? Okay, but yeah, don't sleep during the class, okay? And then job performance, reduced time work, reduced productivity, reduced precision, and the severe one is that absent. You not come to the work, sickness absent, time loss of accident, okay? All right, so now we look at how actually we look the sound itself. Okay, we already know that this is sound, this is noise, okay, what it can affect to us, okay. But now we want to know the sound itself. We want to be introduced with the sound, okay. You can want to get friends with the sound. So this is what you see when I just talk, okay, coming out from this speaker. It's actually that the molecule of the air is being pushed or coming back, push back and then coming back. And this is where I just talked, coming from the speaker. And you see here, there's a red point here that it doesn't go to the microphone here. It is just that it is vibrating like this. It doesn't go that the molecule goes from here to there, no. The molecule of air is only doing like this, okay? So it is vibration actually. And the energy is transferred from here to the microphone and then the microphone will collect it, okay? They collect. Okay, so we've got compression, which is this one. So this compression energy will move towards the microphone while there are other parts that is happening, what we call this as refraction, okay? So we put it inside of this, and what happened here is that you are measuring actually the variation of pressure. Okay, the variation of pressure. Okay, you are not measuring the energy, the temperature or whatever. You're measuring the variation of pressure. All right. So you got atmospheric pressure, and then the energy is coming from here to here. And the variation of pressure is being collected by the equipment. Okay? So we characterize the sound, this line, we characterize it based on speed of sound. Okay? Speed of sound. It is about 325 meters per second, okay, in the normal condition. And then we characterize it based on frequency of sound, I just told you, pitching, or low bass, so we characterize by that. Wavelength, distance required to travel for one cycle. Okay, so if you see here, from here to here, how long it takes to go from here to here, the energy itself. And then we look at the amplitude, which is basically quite related to volume. Okay, volume. All right, so this is the wavelength, okay. So we measure the time taken from here to here, okay, and it is affected by temperature, okay, the condition right now, okay, the condition right now. If you're measuring it inside of the water, you get different kind of wavelength. And then we look at the amplitude. So this is amplitude, and frequency is actually 1/T, okay. So meaning that if I do like this, that means that the pressure is something like this, okay. The time to complete for one cycle is 1/T, okay, which is equal to frequency. Okay, so this is a normal sinusoidal sound, okay. Actually, I can create using MATLAB to create the sound, okay. It's actually like a normal sound. Today is sinusoidal actually, but combination of certain frequency, but the core is sinusoidal. And if you measure it, you can also characterize it based on RMS and peak. So peak is from down here to the top, okay. This is peak to peak, and from the center to the top, we call it as peak. And then the average is somehow in the middle, 0, but usually you put this part positive, okay, and it will be like this, okay, and the average is at about the center, and RMS is a bit high, okay, RMS is a bit high. And from here, okay, this value, we can convert it to sound power level, sound intensity level, and sound pressure level. The one that you measure, that you report, okay, you can use your phone, all right? You can install the software, you'll get dBA. That is actually sound pressure level, okay? Sound itself in Pascal. In Pascal, which is PA. So you convert it into dB, okay, with certain equation. And we measure that, we call it sound pressure level. So there are other two, sound power level and sound intensity level. But the one that we have usually is sound pressure level. All right, so this is the equation, okay? So you're measuring pressure, PA, that is P, this thing, this value, P. And then you divide with PO. PO is a constant value, actually a pressure that you can hear, the minimum pressure that your ear can hear. Anything less, your cochlea or your ear cannot detect. All right. Beyond than this value, you can detect. All right. So you divide with that value. Okay. You logarithmic it, and you times with 20. Then you can get SPL, sound pressure level. All right. It is not dBA yet. It is only dB. Okay. I'll show you why where we can get the A, but it is dB. And then we have other two aspects, which is sound intensity level, this value, and sound pressure level, this value, which also being used in industry. But I guess that at this point you may not want to know. You only want to know the SPL because that is directly what you measure from your handphone. So it's later you can try to find what is that. All right. But so intensity is intensity, and power is, if I talk louder, then you got lots of power and lots of intensity. All right. So that is the relationship. So if I talk louder, the sound power will be high, and it can go farther. Okay, farther, jauh. All right. Sound pressure is pressure. Sound power, you can go very far. Okay. Intensity is just one bit of it. All right. Let's say that I'm talking like this. Okay. The speaker is pointing at you. The intensity is very high. Okay, but the intensity towards the back is very low because you are directing the speaker to you. All right, so that is how the relationship. Okay, but so this is the equation. But as you go from here to there, the sound will get reduced. Okay, so we call it. There's a law governing that. That means that we call it inverse square law. And what does it mean is that if you are measuring here, like it is 90 dBA, okay, as you double the sound, double the distance, the sound will get reduced by twice, okay, by half, sorry. A doubling of the distance from a noise source reduces the sound pressure level by half, okay. There's some text here, some text there, so by half. So if you want to have a machine in this room, okay, with that sound coming like this one, okay, if you want to make sure that your employee is in good condition, you have to put the employee maybe at the back. Okay, maybe at the back, I don't know, where is it, should be. But you have to make sure that the sound is less than 85. Okay, so that is how you actually manipulate it. Right? Okay. So this is the equation. We do not want to go deep. So now we look at analysis and presentation of sound noise data. All right. So far, we have been look at what is the definition of sound. Okay. And then we have looked at the definition of noise. Okay. And then you know what sound and noise can affect you. All right. So you know that if you listen to a sound for a very long time, you can get deaf. Okay. It can affect your mind, give you stress, hypertension. Okay. And you can have miscommunication and the rest. And then you have looked at what is the sound power level, sound intensity level, and sound pressure level. So that is where if you pull out your phone, okay, you install the software, you see dB, dB, dB. All right. So it's actually sound pressure level. Okay. Basically a measurement of pressure inside inside the air using microphone. Okay. Now we look at how we do analysis and presentation of sound and noise. This is where, as consultant or workers who are working with sound will do. Okay. So these are the two basics. Okay. We go to this point. All right. So to calculate sound pressure level, okay, you can imagine right now there's a machine, okay, with a sound like this. All right. So you pull out your phone, okay, or your equipment, you measure, okay. So the thing that the phone is measuring is actually pressure variation. Okay, as I shown to you just now, the pressure will vary from up and down, up and down, up and down. You measure that, and you get pressure, and it is measured in Pascal. Okay, so if you do not know Pascal, then maybe you have to go to your middle school, right? Physics. Okay, it's actually force divided by area. Okay. But yeah, I do not want to discuss about that. It will be too long. Okay, maybe you should find out by yourself how do we get the Pascal. And then you've got atmospheric pressure at 101 kPa. So this is, if I don't talk like this, okay, so the pressure is actually 101 kPa. Okay, so your ear already normalized with that. And then as I talk, it will vary at 101 kPa. So this is 101 kPa. If I talk, the pressure will just be at 101 kPa. So up and down at that point. If you go to higher places, okay, such as, where is the high places here? Bromo. Bromo is high places, right? Or Batu. Batu is high places. Pressure could be a little bit different, but as you talk, it will have the same thing, variation of pressure. But the wavelength could be different, okay, because of the air at the top is a bit compressed, so it will be a bit different. So when we measure sound pressure level, we compare the sound pressure with the reference pressure P2, okay. So the equation is that LP is equal to 20 log P1 divided by P2, and this outcome will give you dB, okay, in decibels. All right. So let's say that you got a sound, okay, you already measure, okay, and you measure it. You found that the sound pressure level is 78 dB. Okay, this is without A. Later I will show you what is A, dBA. Usually in your phone you got dBA, but you can also eliminate A, you get dB. So let's say that you got dB, 78 dB. Okay, and you can actually use the equation previously to know what is pressure. Okay, so when you get dB, your phone actually do some calculation inside of the phone. Okay, there's some equation. All right, there's some kind of DAC, data acquisition. All right, that collect the pressure and give you the final one dB, 78 dB. So if this is a value, you can try to find what is the pressure. Okay, because at one point you might be using that pressure instead of dB. Okay, that is as consultant are doing. Okay, but for you may just want to know about it. If you want to become a consultant in sound analysis, then maybe you should know more and you go to a class. But yeah, this is how we do it. So we divide a value with 0.00000002, okay, which is 20 micropascal. And as mentioned to you just now, that this value is corresponding to the closely similar threshold of human hearing. All right? So threshold meaning that the minimum point that you can hear. For example, for vibration, all right, for your phone, you take it on your phone, you can change the intensity. right? If you put it too slow, you cannot feel it, then you cannot be aware that your text message, you can get it. And then you adjust it to a certain value, and this value, you can feel it, okay? So when text comes in, you can feel it. And that is what we call as threshold of sensitivity, okay? So this point, okay, vibration is different thing than a sound. So this point is 20 micropascals, okay? So when we give you a value of dB, we actually compare it with that threshold. So that's why we divide P1 to 0.00002 Pascal or micropascal, 20 micropascal. So 78 dB is not exactly direct calculation from 20 log P1. Okay, it's actually 20 log P1 divided by 20 micropascal. Okay, so when I inform you 78 dBA, okay, you have to divide the pascal, the pressure, with 20 micropascal. It's not a normal calculation like if you can log P1. Okay, so please put in mind that if you are doing sound. So from here you can get P1 is equal to 0.159 Pascal. So that is actually microphone. You see, this one. There is a microphone over here. Okay. As I talk, okay, it will measure the pressure. Okay, and then your phone will give you the dB. But over here is different things. It's a variation of voltage. Okay, voltage and create the sound. So it's another guest lecture if you want to. But yeah, this is how we do measurement of noise. Okay, so if let's say that you got the sound pressure level of 78 dBA, okay, you calculate the pressure, okay, the pressure that actually the microphone acquired is something like this. So here is 0. It is not 0 actually. It is 101 kPa. Okay, the variation is up and down. Okay, this is 5 seconds. It is too small, yeah? Can you imagine? 5 seconds, all right? And the variation maximum peak pressure is 0.22485. I forgot the unit. The unit is PA, Pascal, okay? While the RMS pressure is 0.159. So how do you calculate RMS? It's 0.707 times the peak pressure. Okay, peak pressure is 0.22. You times it with set 2, then you can get RMS. If mean pressure, this value you divide by 2, you will get 0.11. That's mean. But effective pressure is actually RMS that is equal to 0.159 PA. Okay, and that value you put in inside of this equation and you get 78 dB. So that is how you get the dB. Yeah? All right. Okay, so now this is at a single frequency. As I talk to you, the frequency is varied. All right. So my name. So there are some frequency over there from M to Y. Okay. Maybe at first M is low frequency, Y a bit high frequency. Okay. As you measure it from so it starts towards the end of Y, you'll see that the pressure will be different as well as the frequency. So here is a normal, okay? And then you get a frequency, okay? And because human ear respond to certain range of frequency from 20 to 20K, we have to evaluate it based on the octave band and 1/3 octave band. Okay, there's an azan right now, so maybe we should just stop for a minute. All right, so we continue back with this lecture. Okay, so this is a single frequency, meaning that maybe at 50 hertz, one value. Okay, as I talk to you, the frequencies are actually varied, as I mentioned to you just now, because speech, okay, the sound is like 1 point is very high, 1 point is very low, 1 point is 1 point is right. So there's a variation of frequencies over there. So what we do, so this is one. So what we do, we categorize it into octave band and 1/3 octave band. So this is the range of what we can hear. We divide it into octave band and 1/3 octave band. Okay, and I think it should be here. Oh yeah, this one. I think I got the slides differently. So from 0 to 20 kilohertz, we have this band. Okay, 16 hertz, 31.5 hertz towards 60,000 hertz. Okay, so you see that if you look here, the range is, this is low, this is 22. Okay, there's a wide range over there. But if you look at the smaller one, the smaller value is 16. This is from 11 to 22. You see here is that the size of each band is not the same. As you increase from 16 to 31.5, the range is small for 16. As you go to 60,000, the range is large. Okay, so we do that because we want to simplify sound. All right. And if you look at frequencies, okay, if we do some analysis, all right, so let's say that this value is a single frequency. We add lots of frequencies, okay. What happens is that you will get this kind of sound, okay. It's like so you add lots of frequencies, it becomes like that, and that is where over here you can hear, okay, as I talk A. So A. Alright, so that is where it gets. It's a combination of lots of frequencies that if you add it, it will become like this. Okay? If you use an equation, we call it fast Fourier transform equation, you will know what are the frequencies, okay, inside of this complicated waveform. Okay? So I talk to you. My name is Khairil, okay? So we can measure for each second, okay? And we can know what is the frequency. So that's where AI is being used inside of your phone, okay? That it say, hello Google, or okay Google, it will detect that, okay, the frequencies, all right? So that is where it comes from. You use this analysis and pick it up, the frequencies. But for us, as consultant of noise, okay, or expert in noise to do some measurement, we use this a lot because you do not want to detect the AI, whether you talk whatever you talk. We just want to know whether the noise can affect you or not. So we divide it into this band, okay, and then we apply weighting. So this is where you see A weighting, B weighting, or C weighting, okay. So the A weighting is usually being used for human, okay? The machine, usually we use C weighting, okay? If you want to measure sound from the machine and how it affects the machine, we usually use C weighting, okay? But they are used differently, but yeah, that is what you call it as maybe core things, okay? But for A weighting means that is a point that we feel comfortable, okay? We represent it with A weighting. And this is what you see, the weighting. So weighting is pemberat, okay? Pemberat. That at low frequency, this is 10 hertz, okay? You can only hear 20 hertz, right? At 20 to 20K. So at 10 hertz, the value is negative 670. So what does it mean? That if I talk to you, okay, with this, with amplitude of, let's say, 1 Pascal, okay, The one that you feel comfortable will be minus 70 of 1 Pascal. Okay. It's something like that. So meaning that that this is something related to human comfort. Okay, that I have to measure the comfort level, okay, for across frequencies, and get this weighting. That means that across this A weighting, you can compare it with what is the equivalent comfort for people when saying. So this is the line. So at 1000 hertz, if I talk to you, you got 1 Pascal, and that is what the point I feel comfort. But equivalently, okay, at 10 hertz, it is much less than 1 Pascal. It is minus 70 dBA. Okay, that is how A weighting is being designed. Okay, so you don't have to think about it. You just have to use it. Okay, it's like equivalent comfort counter or equivalent sound comfort. How do you want to hear it? So we use A weighting. So that's where you get dBA. Okay, and then once you measure sound, okay, this is how you apply weighting. Once you measure sound, all right, you apply filter to it, meaning that you divide it into the frequency band, which is 16, 63, 250, up until 60,000. Okay? And then you apply weighting, which is this value. Okay? And then you combine, and then you can get dBA. Okay? So for example, this example, okay, you measure sound. Okay? So once you measure sound, you apply filter, meaning that the sound you eliminate anything beyond than this band. So this band is 135. You eliminate all other than 125 bands, and then you get the sound pressure level of 88. Okay, and you do that the same for each band. You get 88, 89, 90, 90, 91, 87, 86. Okay. And then you apply weighting. So the weighting coming from this table, okay, this table, negative 16, negative 9, negative 3, 0, 1, 1, 1. Okay? And what you do, you just subtract 88 with negative 16, you got 72, and the rest. Okay? And then you combine using this equation, and you get 97.5. That is for dB without A weighting. And with A weighted, you got 96.2. So that is the final value that's coming from your phone. All right? So 96 dBA. So now you know how it comes from. It's a little bit complicated to do. Okay? If you have no background of mathematics. All right? But if you know, then maybe this equation is quite straightforward. Okay, it's just that a filter process is a bit complicated a bit, but usually this happens inside of the phone itself, inside of the SLM, and you just get the value, and that's the value you use. All right? Okay, so how do we measure sound? Okay, we use what we call a sound level meter. Okay, this is quite expensive. It could be around 5,000 USD. Okay. USD, so it is about 25 ringgit Malaysia. So 300 ringgit Malaysia is equivalent to 1 million rupiah, Indonesia, okay, IND. And then you can calculate how many million it should need. But quite expensive, that many people do not have that. So but that's why I just told you, maybe in the second section we'll be using mobile phone, which is quite not that long. Or you can use pressure sensor. Okay, so pressure sensor, you got lots of variation of pressure sensor. And the way to do that will be quite more complicated compared to SLM. SLM, already everything inside of the SLM, you just get the value 96 dBA is straightforward. If you're using pressure sensor, then you have to do all the calculation. That's just like what we did. That's what I just mentioned to you, which is many things, all right? So now we go to the last part of the first bit, okay? So it's 1 hour already. Maybe after this, you got statistics. So legal requirement in Malaysia. So we've got at least 2 legals, okay? First one is factory and machinery. Noise exposure is not being used anymore, okay, because it has been replaced by OSHA. Okay, if you're working in, if you learn about safety and health, you might know what is OSHA, okay, occupational safety and health. But in Malaysia, we have a different kind of OSHA. Okay, other places they have their own OSHA. So this came into force in 1 June 2019. Okay, and then we've got other requirement, environmental quality, motor vehicle noise. But for this purpose of this lecture, I will just show you one regulation, because this is what relates to the ergonomic classes that you have, okay, which is noise exposure. So under this regulation, you've got the objective is to prevent the occurrence of noise-induced deafness, basically to preserve workers' hearing. Okay, so that's why this regulation is there. We want to make sure that the workers in Malaysia, okay, can do not have the deafness, okay, after they are working for a long time. So we got employers' responsibility in this regulation is that to conduct noise exposure monitoring. This is where they call us, okay, to do some tests. Reduce employees' exposure to noise. So once you have done the monitoring, you know whether the sound is high or not, then you apply some kind of engineering, okay, reduce the noise by using engineering administration or PPE. And then they have to do audiometric testing program, and they have to send their workers to learn more about it and establish proper record keeping. So these are the responsibilities. So we usually, for me, maybe they will ask me to do some analysis to advise them on how to reduce employees' exposure to noise. Okay. So the requirement is that there are 3 requirements here. Is that every employer shall ensure that none of their employee is exposed to sound level exceeding 85 dBA. So now you know what is A, how to calculate A, you know how to calculate dB, okay? And this is the value, 85. So if I talk right now, if you have your phone, maybe you can open the app and you can see, is it 85 or more? I think this is 85 or more, okay? But it's fluctuate, it fluctuate. So you cannot expose to 85 daily, meaning that for 8 hours. So usually people working at 8 hours, okay? You cannot be exposed to this amount of sound for 8 hours every day, okay? And then a maximum of 115 dBA, okay? As I talk to you, the sound is going up and down, up and down. Sometimes I kind of push a lot, then the value can be really up, okay? So the maximum cannot be exceeding 150. But this is RMS value, okay? There's another value that the peak. So you remember the sinusoidal wave, take it up and down, up and down. So the peak one at the top cannot be exceeding 140 dBc. Okay? So these are the requirements. Okay? Remember the forklift? It is 87, right? dBA, which means that it is greater than 85. So that is that if a person working with the forklift for 8 hours, okay, the employer has to do something. All right, that is the outcome of it. Okay. If you are using some like hand grinder, the sound is 90 something, it is high, then something that the employer has to do to reduce the sound. Okay. There are 3 ways. One is engineering method, another one is administrative, and another one is PPE. Okay. So if you are so for forklift, okay, For forklift, the value is 87 dB right now that we just shown to you earlier. Okay, so 87 maybe at this level, maybe it's 88. We just assume it's 88. That you can only work for 4 hours. Anything beyond than that, you already exceed 85 dBA for 8 hours. All right. So the value is not like you just double it. So 80 to double is 160, right? It's not like that because you are using dB. Okay. So if you are driving a forklift with sound exposure of 88, you can only work with that forklift for 4 hours. Okay. That means that your employer will have to ask this person to work somewhere else with much lower sound. Okay. So that it can balance that one day for 8 hours, your exposure level does not exceed 85. Okay, so that is how you do administrative actions. All right. Or you can use other, okay, like a change in machinery. So you cannot change forklift just like that usually. Okay, so you do maintain, you do administrative ways to overcome this. Usually for this case is that you got a pump and I have to work really close to the pump and the pump is producing lots of noise. So you somehow change the pump for lower value, lower sound pump, or you put a barrier, or you put an enclosure to it. So you tutup and then sound can be heard, but you have to design properly. Okay. So noise control can be done through PPE. That is the last one that you wear something like a ear muffler. Okay, put it at the ear, then the sound is less. Okay, so that is the least effective. And secondly is using administrative control, like I just told you. So you just work 4 hours, and the remaining 4 hours you work somewhere else. That is also least effective. Engineering controls, that is where you put barrier or enclosure, okay. And then substitution, basically you change the machine to a noise that is less. And then lastly, you eliminate. So this is very hard, that you cannot just eliminate the pump. It is not relevant actually in most cases, but that is the best one, eliminate the sound. Okay, so this is PPE. So you are wearing this. Here you can put something of sound acoustic panels. Okay, this one is enclosure. Inside of this there is a machine inside of it. Okay, there's a machine inside of it. All right. So right now we are still on time. So that means that we got 2 hours. Okay, 1 hour is about ergonomics, another hour is about statistics. If you want to go to taking some, going to the toilet to do something, whatever, to just walk around, you can do, no problem. But we are going to straightforward go to the second part of the lecture, okay, which is about the effectiveness of your mobile phone in measuring sound. All right. So I've shown to you previously. So the sound and noise. Okay. You know, noise is something that you do not want. Okay. You do not want. We know how to measure it. Okay. We measure pressure. We change it into dB. Apply weighting becomes dBA, and this dBA must be below 85. Okay. In Malaysia. Or otherwise, you have to apply some kind of solution to reduce the sound, reduce the noise. So we know that already in this first aspect. As I told you just now, that the equipment to measure sound is quite expensive. Okay, it can be like 5,000 USD. Okay, in Malaysia it's about 25,000 ringgit. A very good one. Okay. If not that good one, then it is not relevant also to measure it. So we have to know that how we can ask all employer to do the monitoring of noise. Okay, under OSHA in Malaysia, they are required to do that, but they don't have the money to buy this piece of equipment. Okay, so we want them to be able to still do that. So one of the way is to use something that they have already, and it is a mobile phone. So we have to analyze the mobile phone if it is okay or not to use for the measurement of sound. Okay? So what do you think? What do you think about it? So do you think that mobile phone has a is good to use for measuring noise? Okay, you've got a phone. It can cost you expensive one, maybe 1,000 USD. Right? It's quite expensive. This phone is quite expensive. It has a very good microphone. But is it good if you want to use it for monitoring of noise? Okay. So previously nobody knows. Now we've got some people who are doing the experiment. Okay. So the one that I have here is I'm referring to a journals that have been published previously. Not my journal, because we are currently still doing it in Malaysia. We have to make sure to know what kind of phones that Malaysians have. And then we have to know who has that phone. Because if you have it, but you are not the person who evaluates sound, then it is not good. You have to ask the employer what kind of phone they have, and then do the test. So it's not the same as at any country, so we have to do it by ourselves. So we do it right now, but other people already did it earlier. Okay, so I just show you what they have done, and maybe you can see, okay, how this can affect the ability of sound, the phone in measuring sound. Okay, in this aspect we are doing. There could be some statistical analysis to be included, okay? And so you can see how these are being related to each other, okay? All right, so without further time, so I just go straight. So this is based on these two journals that we are actually also referring to for the test in Malaysia under National Institute of Occupational Safety and Health, NIOSH, okay? So we've been tasked to do the same, but we have to look at the phone in Malaysia, okay, not in Europe, because in USA they are mostly iOS, okay. In Malaysia we've got some Androids and iOS, and over here I just asked you guys, some of the people here, that you are using Android maybe mostly, okay. So it could be different, all right. So here, so the reason why we want to do is because pocket-sized devices are evolving into powerful instrument. Now your phone is very expensive. It has all the abilities. You use it to play games, right? You use it to do some calculation, to opening a PDF file, to do some many tasks, so call and everything. So it is not a cell phone anymore. It is a mobile computer now. Okay, so because of that, there are people who are designing apps to measure sound. All right, so the ability to monitor sound using readily available technology opens new horizons for research, safety, and creativity. And that is noise monitoring with mobile phones. So I just told you, all right? I just told you. Okay, so I also told you that there are issues with it. So now we look at the problem statement in which we can divide it into three parts. The first is ideal, the second is the issues, okay, and the third one is how to solve it, okay. So ideally is that all industries in Malaysia, they have to do monitoring of noise, because I inform you that there's a legislation in Malaysia that you cannot expose to anything greater than 85, right? So technically, all employer, they have to measure the noise in the work area or workstation. Okay, so they should have what we call as SLM, sound level meter, but this thing is quite expensive. All right, so ideally this is the case, that everybody will have to be able to do monitoring of noise using a sophisticated equipment. Okay, but expensive. They have some kind of other option, which is using mobile phone. So this is the ideal case. So mobile phone can do the task. However, we see that mobile phones, they came with variations. They comes with variation of equipment. Okay, sometimes they have a large storage. Sometimes they have a better processor. You can use it for playing games. Sometimes they have a good speaker. Okay. Sometimes they have good microphone that if you talk, you can hear clearly. Okay. So we've got all these issues: microphone quality, limited frequency range, calibration, variation of mobile phones applications, environmental factors, noise, and lack of standardization, and many more. So these are the issues. So if you want to choose mobile phone for the purpose of monitoring of noise, you need to make sure that this phone can be used. Okay? All right. So how we can do that is that we have to conduct a study to analyze the suitability of smartphones for use as a substitute for traditional SLMs. Okay? So this is where it comes with the statistic. You want to make sure that your phone has the same capability as the SLM. So basically, you are comparing these phones with SLMs. You are comparing the mean that this phone measures with the SLM. So that is where we do the hypothesis testing. We compare this value of mobile phones with SLM, the best one in this industry. Okay? So there are two aspects to evaluate. The first one is based on Android or iOS. So based on the software, which is Android and iOS. It could be others, like if you are using Huawei, you got Harmony OS. Okay? You use Nokia, you got other kind of OS. So that is, in terms of capability, there is other kind of aspect that you have to look at. In this case, we look at only Android and iOS. And then we look in terms of precision and accuracy. I've told you what is precision, but maybe after this I will show you again what is precision and accuracy. And in measuring sound and noise. So the method is quite straightforward, that you identify smartphones that I just told you, that here mostly using Android. But what kind of Android? Is it Samsung? Okay, is it Huawei? Is it Oppo? So what kind of here? Mostly of what? What kind of phone mostly over here? What is the phone that you use? iPhone. Yeah, I just asked the group previously. They said that nobody is using iPhone here. So all iPhone. In front. At the back. Samsung. Oppo. Vivo. Xiaomi. Okay. Any more else? Aquas. Okay, there are varies. There are varies. So we have to a conclusion that there are varies. There are lots of things. Okay, so we have to identify first. Okay, which one has the highest, which one is low, so that we cannot do everything. So we choose like 10 kind of. Okay, so we have to identify not just the phone but also the apps. Okay, because the app is not standardized. All right, so we have to know what kind of apps is good. And then we do experiment in control condition. We do analysis of results using statistical methods. And then we conclude. So that is the process. So the method here, we had these groups of researchers. They went to some field. Lots of students over there. They just asked if they want to be in this experiment. And they found that they have 100 kind of phones. Okay, 100 kind of phones. And the greatest one will be iPhone. Maybe this has been done in the US. Okay, it's like 50-50, 60-40 right now. So iPhone, okay, and then Galaxy, Google, HTC, LG, Motorola, and Motorola. So it's about 65 to 35. 65 iOS, 35 Android. So these are the information. And then they look at what kind of apps inside of these phones. Okay? At that particular of time, they got 1, 2, 3, 4, 5, 6, 7 apps. Okay? 7 apps. So they have to test all the phones with the 7 apps. So you can imagine how many tests they have done. All right? And then to do this is a lot of time. Okay, the student will have to spend a lot of time to install, reinstall and everything. Okay, and then they measure the sound inside of control condition in reverberation room. So supposedly they use it in acoustic room. Okay, anechoic chamber. But in this case, they are using reverberation room, something like this, maybe much more better than this. Okay, and they compare it with a calibrated SLM. Okay, that is what I just told you. The best machine to measure sound is using SLM. And then they do measurement with different kind of sound pressure level. Okay, so 27, 50, 70, and 90. Okay, and then they see how the difference will be. Okay, so the method to analyze, they use two kind of methods. Statistic, but we've got descriptive tests. Okay, descriptive statistical tests. So what is descriptive statistical test? All right, so it's something like mean difference from reference, standard deviation, standard error, and range. All right, and they also use box plot. Do you know what is box plot? Do you know what is box plot? After this, we will see how it looks like. But it has a box inside of the graph. Show Q1 to Q3. Okay, Q1 quarter 1 to quarter 3 of the results. All right, and they also do inferential statistical tests. Okay, there is hypothesis testing. Okay, so you've got condition where you know the standard deviation. Condition you know without knowing the standard deviation. Okay, so if you do not know the standard deviation, you use t-test. If you know the standard deviation, you use Z value or standard normal distribution. Okay, so the condition is that they perform t-tests to assess the difference in mean values associated with each platform. Okay, with the true value measured using the SLM with confidence level of 0.05. So this is what I just teach the class, one of the class about hypothesis testing. You got a significant level, okay, alpha. It can be many value, 0.1, 0.05. In this case, it's 0.05, okay? And because they are measuring in the mean, it is a two-tailed test. So it cannot be less, it cannot be more. So if I'm using SLM, measuring at 70, I do not want it to measure more than what is the value supposed to be, and don't want to measure a value that less than what's supposed to be. So it's a two-tailed test. Okay, it's a two-tailed test. And you can define the null hypothesis and alternative hypothesis. So what is the null hypothesis? All right. The null hypothesis is that the mean of the measured value of sound in all conditions or in each specific condition using each specific phone, using each specific apps should be equal to the mean of sound measured by the SLM. So the mu is equal to the mu. Okay? The mean is equal to the mean. And the alternative is that mu is not equal to mu. Mu of the apps or phone is not equal to the mean of the SLM. Okay, it's a two-tailed test. So I already showed to the other class. So that's this. Okay, so if standard deviation is not known, so you've got three cases. One is case of n less than 30. One is the case of n greater than 30 or equal to 30. Another one is n is less than 30 with population is not normal. So if the population is normal, you use t-test. If the n is greater than 30, okay, with standard deviation not known, you use t-test, okay. If not, then you use non-parametric statistical method, which I don't think that you guys, maybe you guys are learning in the next semester, okay, just some kind of introduction to it, but this is the case, okay. And we've got all the equations, all right, but the one that we use is only this, okay.
which if we make it bigger, you see that the equation is something like this. Okay, so this is null hypothesis. This is alternative hypothesis. Okay, and this is the t value, in which this value you'll be finding it in the table. Okay, in the table. But the process to perform the test of hypothesis, you got two methods. One is using critical value approach. You got state the null hypothesis, select distribution to use, in this case t-test, determine the rejection and non-rejection regions, and then you look at the test statistic value, which is t, and make a decision. So this is the process, but we are not going to do all the process here, but it's just like to refresh your understanding on this aspect. Okay, so we look at the efficiency of the mobile phone. Okay, so they measure 4 conditions. Okay, first 27 dBA, second 50 dBA, third is 70 dBA, and the last one is 90 dBA. For each of the condition, they measure 368 times. Okay, so how many? If you combine all, 300, 300, 300, it's already 1,200. It may be 1,500 could be, okay? Tests. So imagine how long they took to do this, okay? So do you have project, final year project? So you can think about it. All right? And then from all the values, okay, they measure not just one, they measure with the SLM. Okay, the machine that I just showed to you, the device, and they compare the value. Let's say that my phone measure 71, SLM measures 70, so the difference is +1, right? And they do it 368, and they then divide it with 368, they get mean. So this different, they calculate the average of it. Now you got mean difference from reference, which is 5.33, 2.09, 1.33, and negative 3.57. Okay? So that means that the value of 300 times that they test has an error of about that value. Okay? Different value. Okay? Different error, different standard than the SLM. And then they calculate the standard deviation, standard error, and range. Okay? That means within the 368 values, for let's say 90 dBA, there's a range of 51. There could be one phone that measure 90 plus 50 is 140, right? So there could be one phone that measure, it should be measuring 90 dBA, but it measured 140 dBA, right? I mean, that's wrong, right? That's wrong. It's not good, right? I use my phone, right? In this test, it shows that 5.33. But what kind of phone is it? All right? Is it my phone? Okay. Maybe my phone is showing 140. It's not reliable at all, right? But that is what statistic, yeah? So you have to be aware how to use statistic, okay? So you got standard deviation and standard error. So standard deviation will affect the precision, the taburan data, precision. Okay? Standard error affects the accuracy. So what is precision? So this is precise. That means that you measure 4 times, everything is within this area. Okay? If you calculate the average will be this point. This should be the target. This is SLM. So precision, the standard deviation is small, okay? But you need to have accuracy, okay? So what is accuracy? Accuracy is this one. You can measure okay? If you measure 70, maybe you measure 72, 71, 69, 68. If you add it up, you average it, you will get something that is accurate, that is 70. So that is accuracy. But you see, the value is not 70, it's 72, 71, 68, and 69. It's not 70, all right? So you need both accuracy and precision so that it gets to this point. So you have, it is precise, it's 70, and at the same time, you measure 10 times, it gives you 70.1, 70.4, or 69.9. So it's very close. So you need something like that. Okay? So if you look here, the standard deviation is 9 dB, standard error is 0.5, range is 58. So if you see from this value, it means that all the phones of 368, they have lots of deviation. And maybe it is accurate, right? With the standard error from this value, then maybe you can have some kind of zero. You can just make it accurate, but you cannot change the standard deviation. You cannot change the precision. Okay? And with the range of this large, I don't think that we can use mobile phone. All right? So this is a general results. Okay? General results. So, as I told you, this is value that you want to do. So this is descriptive statistical test. You look at the mean, standard deviation, standard error, and the range. Okay? So after this, okay, if you want to do some tests, all right, you have to look at all these values because it gives you some understanding of the data. All right? Okay. So this is what I just told you. So here the standard deviation is large, standard error may be small, range is very large. If you plot it in this figure, so you've got 27. So you can see that this is the variation, and this is the minimum and maximum, the range. This is the range, this is the range, this is the range. So down here is a reference value. You've got 4 values. This y-axis is the values that measured by the phone. Okay? So this is 27 dBA, this is 50 dBA, this is 70 dBA, this is 90 dBA. What you can see here is that phones, they cannot measure it precisely or accurately. Okay? Lots of variation here. So you need all the values to be at this point. You need all the values to be at this point. You cannot have some values at the top, some values at the top. You need to characterize the phone. Okay? And in this case, it's a general result. So maybe more things have to do to classify which phone has less accurate precision and accuracy, and which phones are not precise and accurate. Okay? All right, now we look at the statistical tests. Okay? So over here, you got 4 conditions, 27, 50, 70, 90. We got iOS, we got Android. So iOS is 263 times measure, okay, out of 368. So 263 are iOS, were iOS, and 105 Android. And then you've got a mean of 35 for iOS and mean of 24. The target is 27. Okay, the target is 27. And a mean difference of 11.3, okay, for both. But as you increase the SPL, some pressure level, to 90, at some point the mean difference is almost small, okay, almost 0. At 70 dBA, the mean is 71 for iOS, 70 for Android, so the mean difference is close. So you need to have a value of 70, so here it measures 71. So that means that an error of 1 dBA. But if you look at the standard deviation, it's quite high at first, reduce, but for Android it's almost similar, 9, 9, 9, and 8. For iOS it's 7, 3, 4, and 5. So there's a smaller standard deviation in iOS instead of Android. Okay? And then with standard error of this, and now we see the test statistics, which is t value. Okay? So you remember that we have to calculate t value. Okay? You have to know the rejection rate, but over here we don't have the rejection region. We don't have the rejection region, but we have the value of t. Okay? and convert it with p-value, and you get this value. So for a value to be, for p-value, it must have value of greater than 0.05, 0.5, okay, 0.5. 0.05, and in this case, you got alpha level of 0.05, so rejection rate will be divided by 2, so rejection region will be divided by 2, which means that it needs to have p-value of 0.025, okay, 0.025, so you got to have that value. So over here it's 0, p-value 0, 0, meaning that it is really small, that it is beyond the exception region, okay, non-rejection region. It is in the rejection region, which is really high, okay, or really low, whatever value. However, for 70 dBA, the p-value is 0.48, okay, which means that the null hypothesis is accepted, okay. Which means that generally, if you're using a phone, you measure at 70 dBA, the value could be close to SLM. Okay, could be close to SLM. Okay, so this is the outcome of statistic. All right, but if you look at the mean difference and standard deviation, I think we still need to know more about the results. Okay, but we are using 0.05 alpha level. Okay, for two-tailed test, I think we have to do something with it, because in reality, a difference of 9 or 4 is not acceptable actually. Okay, if you measure 70, you need it to be either 71 or 72 or 69. It cannot be like 77. Okay, that is far. It's like in pressure, it's about 90% value pressure of greater than 70. Okay, so it's not actually correct, even though the hypothesis test says it otherwise. All right, so you need to think about it. When you do statistic, it's not always whatever the outcome of statistic is true. As I told you, there are two kinds of mistake, type 1 and type 2, and you've got to be careful with it. All right, so this is the outcome of the results. So this is a test, p-value and t-value. Okay, and then they got a lot of other tests. Maybe we can just show some of it. Okay, so iPhone, okay, measure with mean of 8, 3, 1, and -2. Large standard deviation and large of range. I think at all times you cannot have range of 30, meaning that if you measure 70, 30 is plus 30, that is like 100 dB. It's already beyond the legislation of Malaysia. Malaysia is 85. Right now you measure 70, okay, the range is 100. So you see that it's either yes or no. The employers shall now do some kind of measurement, elimination of sound. Actually, it's 70. It measures 100. You see? There's a mistake, a large mistake. You cannot have a range of 30, even though the hypothesis test says otherwise for 70 dB. Okay? And then Galaxy is more range, high range, and Google high range. Okay? So that is what you should see. Okay? This is apps. Okay? So for apps, some of the apps has a range of less than 7 dB. This is less than 7. Okay? Except for 70. So this app, SPL and FFT, range is very high. Okay? This is also very high. If you ask me, if you want to use maybe this app, at least for most of the cases, the range is about 6. Okay? So if you're measuring, except for the 70 dB, at least you measure 90, you know that it could be either 95 or 85, right? Which is still okay, okay? But not accurate and not precise, right? Okay. And then we've got this is a box plot, all right? And this apps, 1, 2, 3, 4, 5, 6, 7 apps. This is a range, okay? This is a range. you need this to be really small, like this one. But I think this one is is the first app. This app, okay. And this is results for. I think this is general result. So this is the result. I guess that the first app, SAA Lite, is okay to be used, if you ask me. But still, there are mistakes that you have to take into account whenever that you use it. Okay? So large variability for this one, this one, this one, and this one. This box plot, this is Q1, this is Q2, and anything beyond that could be outliers. All right? Okay, so now we are at the end, the conclusion. All right? So we've got noise now. Is it noise or is it sound? Noise, yeah? Some of you maybe sound because they like the sound. Okay, the music. What kind of music is it? If you know that, then maybe it's a sound. All right? If it is unwanted sound, then it is a noise. All right? So now you know what is noise. Okay, we got a very application right now. So generally, the mean difference from reference exceeded the requirement to be either classified as class 1 or class 2 SLM. So all the phones, apps, we cannot use it. Okay, because there's a standard to classify it as 1 or 2. Even though the hypothesis says otherwise, yeah? Even though the hypothesis says otherwise. And this is the hypothesis testing. 27, 50, 90, reject. 70 dBA, no hypothesis was accepted. Even though that is the case. So maybe some hypothesis testing, you have to change how the use of hypothesis. Maybe a different kind of significant levels. All right, and the rest. Okay? So the one that they do is this. All right? Okay, we have looked at the ergonomic aspect of sound. Okay, how sound can affect you in terms of workload and everything. We have also used some kind of test, statistical test, to do a test on mobile phones, okay? And I think that you can now kind of integrate that both. Yeah, you see how they are being integrated. At one point, you are doing a project. You might want to integrate your knowledge, and in this case, statistics and ergonomics, all right? But whenever that you want to do ergonomics, you might want to, when you look at a one pit, okay, you have to further learn about it. So you remember that you got a test to measure oxygen consumption. In the class, you are being told like that. But if you want to do the experiment, you have to further understand it. So something like what we just did. So if you want to know what the sound, you have to know all this before you do the test. Okay? It is the same for you guys. And I hope that whatever that I've talked is something that beneficial for you. Any question? All right.
Thank you for the time, sir. I would like to introduce myself. I'm Aurelia from CE class. I would like to ask regarding about sound and noise. So we have our lab report, right? Sometimes when we do our lab report, we listen to music, and we know that one of the effects of either noise and sound is it might decrease our concentration. But in this case, the music that we are listening to, it's actually pleasant to our ear, and it's not unpleasant, so it's not included in noise. But sometimes at some point, it may decrease our concentration in doing the lab report. So maybe do you have the tips for that regarding we can listen to music while doing something, but it actually do not decrease our concentration. Thank you.
Okay, hello sir. My name is Muhammad Rehan from English. I just want to ask about the noise level like that. Is there any difference between the noise tolerance between men or women worker? The difference noise tolerance between the men or women worker?
Oh, between men and women. There should be, okay, a different threshold, all right?
Test. Okay. Okay, can we take photo together with the student lectures and Dr. Hairil Anas? Okay, we take the photo first with the background there. There. Student first. Okay. Oh, you want to sit? Maybe we take the seat into the center or what? Maybe we take the seat to the center. Okay, everyone. Maybe you can move forward to fill the blank seat. Okay, let's take a photo. Everyone, attention. 1, 2, 3. Cheese. Again. 1, 2, 3. Yay. Okay, and then we take one more photos. So everyone, please move forward. We take with the backdrop in the front. So move forward. Yeah. Pak Khairul di tengah. Jadi Pak. Iya. Soalnya test. All the students, please move forward into the front, to the stage. Oh. Duduk. Duduk kan. Itu depan dulu. Iya, apa sih karpe Kak? Mau Pak Khairul di sini, nanti anak-anak belajar di depan. Oh. Okay, first. Oh, maybe so. Yeah. With the sun. I'm sorry. So we take photo one more time with Mr. Hairil stand up with the lectures. Kayaknya